Welcome to the last review lecture. We are going to review the final chapter, the fluxes under simultaneous multiple driving forces. When we began the review, I had shown you this, right? This pretty much gives you the crux or the essence of the entire course. If you look at the flux of a quantity, primary driving force constitutive equation, let me just quickly run through this. We have already discussed this. We looked at concentration gradient as the primary driving force for mass flux and a constitutive equation, the fixed law, the velocity gradient as the primary driving force for momentum flux, Newton's law as a constitutive equation, temperature gradient, the primary driving force for thermal energy, Fourier's law as a constitutive equation, electrical potential gradient as the primary driving force for charge flux with Ohm's law as a constitutive equation. Okay. So, you can see the relationship between the various fluxes, the forms of equations are all similar which relate this and this, and the forms of even the constitutive equations or examples of constitutive equations are also very similar. At least the simplest constitutive equations are all very similar in their form. Okay. Only thing is that the details are different. So, this is so far in the course, and in this chapter we are going to look at multiple driving forces causing a flux or multiple fluxes. So, we said there are a few couple of ways by which you could approach this. One is, since the fundamental equations were conservation equations, conservation of conserved quantities or conservation of conserved physical quantities, that is what was represented in equation of continuity, equation of motion, equation of energy and the charge conservation equation. Therefore, they should certainly be applicable. So, if there are multiple driving forces, you write down all those equations and you could simultaneously solve them. In principle, it should work. Okay. However, practically the mathematical complexity could be very difficult, could get very high, and the solution could get very difficult, and therefore, we use a slightly different approach, which is called the transfer coefficient approach, right? You have a mass transfer coefficient, heat transfer coefficient and so on and so forth. You could do that. Okay. So, we started by looking at an important aspect of mass flux under the influence of both a potential gradient and a concentration gradient. We spent a good amount of time on that. Before that, the mass flux could arise due to a concentration gradient, electrical potential gradient, pressure gradient flow, as well as the temperature gradient, natural convection. Okay. Out of which we chose to look at two in this. Yeah, these were the approaches: mass flux, heat flux and so on and so forth, mass transfer coefficient, heat transfer coefficient and so on. Okay. When the concentration gradient and electrical potential gradient case was very interesting. We started looking at the mobility of ions in solution. We started with very basic definitions and got to the Nernst equation, which gives the relationship between the potential difference between 2 points involving charges and so on and so forth, involving charge transport, and the concentration of the ions at those two places. So, that was we looked at electrodiffusive equilibrium on our way to the Nernst equation, the Einstein's relationship between the diffusivity and molar mobility, and then the basis for our electrodiffusive equilibrium. Then this was our Nernst equation. Okay. Nernst equation, of course, is a very useful equation. We saw various applications of the Nernst equation. Whenever there is electrodiffusive equilibrium, Nernst equation is valid. So, then we saw the mobility of ions across a membrane. We saw how the Nernst equation could be used. Just the presence of a physical layer does not really matter. Nernst equation must be valid. However, in a real membrane, when you have multiple, or even in any membrane, you have multiple charges distributing themselves at the same time, as it happens in the case of neuronal membranes. That is the basis for us, our senses to work, and so on and so forth. Then we looked at some approximations that will work very well for analysis, such as Donen equilibrium approximation, where the transport of individual ions are taken to be independent of each other. Right. So, then we got some useful relationships there, the membrane potential and so on. Then we worked out some examples also, very straightforward examples in this case. This is what Donen equilibrium was. Multiple ion types, they distribute at the same time, then assume that the currents of each ion are independent of the other ions. So, that is the basic idea. Then you could write the relationship between the ratios of these various ions at equilibrium. The membrane potential ideas we saw there. Then we looked at the electrical circuit representation of a membrane. We said that the membrane consists of the lipid bilayer, which is nothing but charges separated by the lipid part, which can be considered a dielectric. Therefore, that is a typical capacitor. And then the ion channels, which cause the passive flux of ions across them. Active transport is not a part of our models, not a part of our consideration in this course. So, the passive transport can be modeled as a resistance and the Nernst potential combination, and so on and so forth. Then let me at least briefly show you what those what the representation looks like. Yeah. So, the membrane has been converted into its electrical equivalent. So, you could apply electrical principles to analyze it. So, this is the lipid bilayer membrane, a capacitance. This is the ion channel for sodium. So, this is the conductance of the ion channel and a Nernst potential for sodium, conductance of the potassium channel and a Nernst potential for potassium. The intracellular part, the extracellular part, intracellular minus extracellular is taken as the membrane potential delta Vm, Vi minus Vo. We had seen this, and then we worked out some relationships between the ionic currents and the membrane potential, and so on and so forth. Okay. This is the resting membrane potential, ion currents, Nernst potentials of the ions, if only potassium and sodium are involved. Excuse me. We also worked out some examples there. Then we looked at the action potential, which forms the basis for all our senses. It's nothing but the dynamics of the ion transport across a neuronal membrane. We looked at sodium and potassium alone, and that's good enough for most situations. Bring in calcium at times, and so on and so forth. So, we looked at the basis for action potential and how a series of action potentials can arise in a very short time of a few microseconds across the entire length of the neuron, and that results in the axial current. And that is how we are able to sense or react. Then we applied showed the applications of these principles to electrophoresis, which is an important process either in the lab or in the industry. Electrofocusing is an important process in the industry. The principles were shown. Okay. So, this is what we did for the situation where there is a concentration gradient and an electrical potential gradient at the same time. Okay. Very many applications. Some fundamental aspects we had covered there. Then when we looked at simultaneous concentration gradient and velocity gradient, here we looked at the case of the blood oxygenator, where there is a thin layer of blood that flows and oxygen from the air oxygenates the blood that goes through the blood oxygenator. Of course, all this is kept in a sterile box and so on and so forth. We analyzed the situation here through an equations approach, and I also used this to tell you something about modeling itself. Right. I think this was the example that I had used. Yeah, the above model falls short in agreement with experimental data. Right. So, this is essentially the way the modeling goes. Model is a representation. Of course, we cannot represent everything. So, we represent the salient features of the physical system. That is tested by testing the model results against experimental data. If it is good, fine, we are happy that we have captured the essential aspects of the system through the model. Otherwise, we need to go back and refine the model. In this case, some of the reasons why this is happening, the disagreement is happening, could be because the reaction between oxygen and hemoglobin has not been considered, as well as the fact that the blood has been approximated as a Newtonian fluid. Right. So, this is an important aspect that you need to pick up for any mathematical modeling. Then we delved into the transfer coefficient approach, first for the case of simultaneous concentration gradient and velocity gradient. We spent a good amount of time on the bioreactor KLa, which is the oxygen transfer ability of the bioreactor, in this case of a biosystem, which it's something like this. That's a bioreactor there. So, we are using this approach here. Mass flux equals mass transfer coefficient times the concentration difference. And then we elaborately derived the case of transport from the gas phase to the liquid phase. The phase 1, phase 2, gas and liquid. Elaborate derivation here. So, what this gave us was a quantity called the KLa, KXA, which is referred to as the KLa, which is the volumetric mass transfer coefficient. The volumetric, it indicates the ability of a bioreactor to provide oxygen to its culture. And it is an important parameter, we said. Pretty much it's measured before every bioreactor run, whether in the lab or in the industry. And I also showed you how you could estimate KLa by the dynamic response method. I discussed the dynamic response method in some detail. Sulfide oxidation is an old method, we did not discuss it. Also, I mentioned that we need to be careful with the name. The dynamic response method refers to different things in different textbooks. This is something that is common across many textbooks, so I had used that. And also, we had used an intelligent system, or a very insightful system, broth minus bubbles, to get at simplifying the balance, to get at a useful relationship, to estimate KLa from experimental data of oxygen sorption onto a system, onto a liquid system, the bioreactor system, that is. We also worked out a problem to show how you could get to KLa from relevant data. This is from my PhD days, my own data. Okay. That was for the problem. Okay. Then we talked a little bit about the, quite a lot about the liquid phase oxygen supply strategy, where you have a generation term also coming in through hydrogen peroxide and so on and so forth. Then I went off into the research significance of transport principles. They are principles, they can be applied anywhere. I gave you a flavor of how they were applied to get to some very meaningful aspects in our own research. I think I discussed about 4 or 5 papers, starting with the LPOS paper and all the way down, including the one of the recent papers on which had used the principle of pseudo steady state approximation to get at very meaningful insights, which can also have the ability to transform the way medicine is done and so on and so forth. Okay, that's what we talked about. Okay, you can go and refer to those papers, get more out of it. If you have any comments or questions, please raise them in the Ask a Question forum. Then we went back and looked at concentration and velocity gradients, velocity and temperature gradients from an equations point of view. Yeah, we have some time, so I can probably tell you that. Yep. First was the application to the enzyme immobilized on a non-porous surface, the kinetics of that, the process kinetics of that. Okay. We said that, okay, let me go to this picture and talk to. We said that this is a slab, a rectangular, a cuboidal slab that sits in the liquid. So, it is a rectangle in section. So, you have an enzyme that is immobilized onto the surface of the slab. You have a substrate that goes from the bulk to this enzyme crossing the liquid solid film, and then the product that moves out. Okay. There is an aspect of transport associated with substrates moving from the bulk to the interface, and then the product moving out, and then there is an aspect of the reaction itself. These two have certain characteristic times associated with it, and the process time depends on the characteristic times of transport and reaction. So, which one is important can be inferred from what is called an effectiveness factor. The Damkohler number gives you some idea in terms of a general view and so on and so forth, and Thiele modulus gives you some idea in terms of extremes, the view of extremes in that particular situation, whereas effectiveness factor gives you which one is more important. To get to such insights, we had used the transfer coefficient approach for one, compared it with the reaction rate. Right, we had gone through the derivation. Effectiveness factor is the ratio of the observed reaction rate to the reaction rate in the absence of mass transfer resistance, and this is what gives you all the insights that I just spoke about. Okay. Then we continued with the equations approach for simultaneous temperature gradient and velocity gradient. In this case, it was heating of a protein solution in a horizontal cylindrical tube. We said we needed to solve the equation of continuity, equation of motion, and the equation of energy simultaneously. Then we did that and got an analytical solution, at least for the limiting case. I also mentioned that you could get you could also use numerical methods to solve them if you have the skill, or if you can team up with a person with the right skills to in numerical solutions, numerical analysis, numerical solutions, and so on and so forth. Okay, then we saw the occurrence of the Reynolds number and Prandtl number in most of these forced convection situations. These are non-dimensional numbers which have great significance. We already know the significance of the non-dimensional numbers. Okay. And I think after that we got into the last part, which was using or taking the transfer coefficient approach. We used a heat transfer coefficient for design of heat exchangers. Heat exchangers are important equipment in the industry, and there are principles that govern it, although they are the size of rooms, entire rooms and so on and so forth. There are principles that govern these, and some of the principles we saw in this course. We took an example of changing the temperature of an algal broth that had heated up by passing through the photo section, right. Okay, that is the example that we took to provide us with the context in which to pick up these principles. So, we had as a result looked at co-current flow, counter-current flow. Then this simple equation was the basis. H A delta T is the heat transfer rate. We saw different kinds of heat transfer coefficients, and that it depends on the kind of temperature difference that we are talking about and the kind of areas that we are talking about. There are three different types: the heat transfer coefficient based on the initial temperature difference, then the heat transfer coefficient based on the arithmetic mean of the temperature differences, and then the heat transfer coefficient based on the logarithmic mean of the temperature differences. This is preferred because it depends less on L by D and so on and so forth. Okay. Then a differential approach was introduced. Then the a basis for heat exchanger design was presented. This was the starting point. The total resistance of the various resistances in series were considered, and then we wrote down expressions in terms of the heat transfer coefficient to back out an overall heat transfer coefficient, and there are two types based on the outer area of the inner pipe or the inner area of the inner pipe. So, all that we saw, and then once you know that, it is nothing but you can get the heat transfer rates just by U naught A delta T. That is it, as simple as that. So, we came down to the fact that once you know the individual heat transfer coefficients, then you can get the overall heat transfer coefficient. The individual heat transfer coefficient, you have a different correlation for different conditions. For example, we talked about the correlation for highly turbulent flow under certain conditions and for laminar flow under certain conditions, two different expressions here. And I also mentioned in general that there are different correlations for different situations. Free convection has a different correlation, phase change has a different correlation, condensing liquid has a different correlation, cooling liquid has a different correlation, and so on and so forth. So, different situations you pick up different correlations and then use to find the overall heat transfer coefficient, and that is where we finished up the course. Hope that you found the course useful. Hope that you also had fun. Don't worry about the mathematical complexity if you are not oriented towards mathematics. If you are, then you had enough food for perking your interest and so on and so forth. So, hope you had fun. Hope all of you had fun. If at all you need anything anytime, please feel free to write to me. Okay. You know the communication details. An email should be fine anytime. Wish you all the best. Let us sign off here. Bye.